Bam! Mr. Tarrou. In this video, we're going to do 3 examples finding derivatives of functions that involve sine and cosine, basically finishing up the rest of our basic derivative rules. So we just got done talking about some basic derivative rules, basically the power rule, where all of our expressions were kind of algebraic. Now we're going to move on to trig. We're soon going to be learning about the derivative rules for secant, cosecant, tangent, and cotangent, but those rules can either be memorized, but even better, we'll be able to derive those on our own when needed, using the product and quotient rule for finding derivative. But we're not there yet, so let's focus on here. We're going to be looking at a graphical comparison between the graphs of sine and cosine. Both have them written in orange here, but we're going to do the sine function in orange and the cosine function in green and see how they're related and kind of see why one function is kind of giving you the slope of the other function. It's always a good idea to keep looking and be reminded about what a derivative function looks like in comparison to the function for which it is giving slope. Really important in AP. We're also going to then be, like I said, be doing 3 examples. The first 2 are up here, kind of straightforward. The third example, we're going to be finding a derivative of a function and locating the point where we have a horizontal tangent line, and that'll be the end of the video. The timestamps of those examples are below, along with links to my channel's homepage and website, where you can find all of my 700 plus math videos to date, covering Algebra 1 to Calc 2 and AP Statistics. Okay, we do definitely in calculus want to really, without even drawing, be able to see the parent functions for sine, cosine, secant, cosecant, tangent, and cotangent. That's really going to be helpful for us to be able to do all of our homework, but especially just an idea of what the graph looks like can sometimes answer a calculus question. So we have an independent variable that is going to be describing basically theta or x, and a dependent variable of y. And theta doesn't match this notation, but we have here on the unit circle, when you put in 0 radians into the unit circle, an orange for sine, and the sine of 0 radians, y over r, is going to be 0 over 1. So the sine of 0 is equal to 0. When you rotate pi over 2 radians, and you're looking at 90 degrees, but we don't do or work with degrees in calculus, the sine of pi over 2 radians is going to be equal to 1. As you rotate halfway around the unit circle, the sine of pi is back down to 0. Then the sine of 3 pi over 2 is negative 1. And the sine of 2 pi is 0. And just finishing this pattern up, which of course by now we should certainly, though I just kind of reviewed it, know what the parent function for sine looks like. And it's something like this. Okay, so there is a portion of a sine wave. Now in green, hopefully we're going to be able to see these colors on camera, we're going to be talking about or looking at the equation y is equal to the cosine of x. Now with cosine of an angle measure giving us a ratio of x over r off the unit circle, almost looks like a V, in the unit circle having the radius set to a constant of 1, kind of like the x-coordinate of a unit circle is around the unit circle is just going to be cosine. So the cosine of 0 radians is an x value of 1 or over a radius of 1. So of course we know the cosine of 0 radians is 1. The cosine of pi over 2 radians is going to give, you're right above the origin, so our x-coordinate is 0. The cosine of pi radians going halfway around that unit circle is going to give us an answer of negative 1, and so on and so on. So we have 1, 0, negative 1, 0, and 1. I can just use those nice round integers or round values of negative 1, 0, and 1 because I've marked off the beginning of our phase shift, which we don't have any with parent functions. The end of our period for sine, cosine, secant, and cosecant is 2 pi. The period for tangent and cotangent, because they don't have r as part of their ratio, those only have a default period of pi. But we have now a sketch. Some of you might think I don't need to talk about the shape of parent functions in the beginning of calculus, but I can tell you right now, after years of teaching calculus, we still, we all forget things, and we need a refresher of this knowledge as we move into our new course of calculus. So we have y is equal to sine of x, and we have cosine, or excuse me, y is equal to the cosine of x. Now, it says here, it should be a different function name. It says here that cosine is the derivative of sine. So if y is equal to the sine of x, then I can say that while I'm calling just this green graph here the cosine of x, which it is what I graphed, but it is also equal to y prime. And remember what a derivative function tells us. If the original function is sine of x and we're being told that the derivative of sine, or y prime, is equal to cosine, then the answer that we get from a derivative is the slope of the function from which it's derived. Now, we didn't derive this necessarily by walking through the power rule like we did in the previous lesson, but it is given to us as fact. Now, what we can see here is from, I can make this a bold orange section here, from negative pi over 2 to positive pi over 2, through this interval, the sine function is increasing. Now, if a function is increasing, its slope is going to be positive. And indeed, we see the green graph, it's a graph of cosine, but it's not just a random graph, it is a graph of the derivative of sine. That derivative function is above the x-axis, yielding positive answers. And those positive answers, the dependent values that we're getting from the derivative, is the slope of the function from which it's derived. So if your function is increasing, your slopes are positive, thus the derivative is above the x-axis. We have a place here at negative pi over 2 where the sine is not increasing or decreasing. We have a horizontal tangent line. Actually, at many places, but centered around the origin here, we have a horizontal tangent line at x equals negative pi over 2, and at x equals positive pi over 2, we have the what appears to be the steepest or the fastest that this sine function is increasing is at that x value of 0 radians. And indeed, since it looks like it's the steepest here, we're getting, yes, the largest y value, the largest answer from our derivative function. And actually the slope here for sine, this, you know, the slope of the sine function when x is equal to 0 is equal to 1, the value that we get from that derivative function, and so on and so on. As the sine function starts to decrease from, or on the interval from pi over 2 to 3 pi over 2, that decreasing function for sine is yielding negative answers from the derivative, which is the cosine of x. Over here, we have the cosine. I don't know how much I can more add to this. We're going to just start scribbling all over the place. But the derivative of cosine of x is equal to the negative sine of x. Maybe I can do this. Let's do this in yellow. Hopefully this is going to show up. So if we have cosine of x in green and negative sine of x, if we look at our sine wave and reflect it over, with this negative leading coefficient, reflect it over the x-axis, where the sine function is 0, it'll remain 0. Where the sine function is 1, it's going to become negative 1. And here in yellow, maybe I'll do that all in bold. We see that, hey, where the cosine seems to have a horizontal tangent line, its derivative is giving us an answer of 0, where the cosine function is decreasing. The values of y are getting smaller as the value of x increases, as that cosine decreases from an x value of 0 to an x value of pi. That is reflected with, again, that now bold yellow graph, which is the derivative of cosine, or negative sine of x. we have those negative values coming from the derivative reflecting the negative slope for which the cosine function has. So I hope that kind of helps. And again, it's just one more time we're going to be looking at the graph, graphically comparing what the derivative looks like versus the function from which it was derived, or it's supposed to be representing, giving its slope. Now, over here we have g of x is equal to, hopefully not at home going, please get to the examples, but you got those timestamps to jump ahead. So if g of x is equal to a constant of pi times the cosine of x, well then g prime of x is equal to the derivative with respect to x of pi times the cosine of x. And if you're just seeing this and moving into this, all of this process of finding derivatives, you may or may not need to do this, but we can take that constant multiple, use that property to move it out in front of the derivative notation and say that's equal to pi times the derivative with respect to x of the cosine of x, and the derivative of cosine is negative sine. So our final answer is going to be that g prime of x is equal to negative pi, negative coming from the derivative of cosine is negative sine, negative pi sine of x. Excellent. That's example 1. Example 2 is f of theta is equal to 3 times cosine of theta minus theta. This may be the first time in a long time you've seen a Greek variable as your independent variable. That is normally reserved for angle measures in mathematics. So we have, let's write the notation a little bit differently this time. We're going to write the derivative, we're going to take the derivative with respect to theta, not with respect to x, okay? You're not always taking the derivative with respect to x. We're normally, unless you're doing implicit differentiation or maybe arguably even maybe chain rule or related rates, the variable with which we're taking a derivative of is often, though not required to be, the same as the independent variable. When these end up being different, we're going to have to be talking about chain rule, which we haven't done yet. So our independent variable is theta. We're going to be taking the derivative with respect to theta on both sides. So what do we have? We have, if I had a y here, I might write like dy d theta, but I'm going to write f prime of theta. The derivative of cosine, once again, is negative sine. So instead of 3 cosine of theta, we're going to have negative 3 sine of theta. This theta is theta to the 1 power. So we're going to bring that power of 1 down, reduce the exponent on theta to be 1, anything, or excuse me, 0, and anything to the 0 power is 1. So the derivative of theta with respect to theta, and indeed if I were to bring this d over d theta into the parentheses, it looks like distributive property, but really kind of technically isn't. It's the sum and difference property for taking derivatives. And you have that d theta over d theta kind of, it's not really, again, this is a calculus notation, it's not a notation for division, but it looks like answer is 1, and indeed it is. So the derivative with respect to theta of negative theta is equal to negative 1, and that is the end of our second example. Now our third example, let's just get that going. So you saw me write it, but we're going to determine the points, if any, where the graph of this function h of t is equal to the square root of square root of 3 times t plus 2 times sine of t. Identify or determine any points where that graph has a horizontal tangent. Now, a horizontal tangent, right, if you're reading a graph left to right, reverse, left to right, where a function has a horizontal tangent, it's neither increasing or decreasing. So we're going to be looking for what? We're going to be looking for the slope is equal to 0. For a very long time, I hated using the independent variable of t, and I kind of don't like to still. My notes have h of t, and then everywhere else I wrote x. If you don't like using the variable of t in your problem because it ends up looking like a plus sign, don't just change it to x. AP and probably your teacher is not going to like that. Now you can say let t equal x if you really absolutely have to change the variable, or just put a little tail. at the bottom of your t. Okay, so h prime of t. Now we're taking a derivative with respect to t. The power on the 1 is going to come down, get multiplied to the square root of 3, and then we're going to reduce that power by 1, but t to the 0 is 1, so the derivative of square root of 3 times t with respect to t, I don't normally write it. Now I'm thinking maybe I should just because we're starting off. And yes, you're taking the derivative of each of these terms individually. It's going to be the square root of 3. We're going to keep that 2 out front, and the derivative with respect to t of the sine of t is the cosine of t. And that is, textbooks often do not put the variable going into a trig function in parentheses. I hate that. I want to make sure that I understand the full expression, which represents the measure of an angle, which is going into that trig function. So we have h prime of t is equal to, again, square root of 3 plus 2 times the cosine of t. Now we're asked to find the points. Now again, and also don't forget to pay attention to what the direction asks for. We're not asking for a location along the x-axis. We are asking for a complete point or points, or maybe there's no answer, where this original function has a horizontal tangent line. Basically, we're being asked to find the point of tangency. That means we need to set the derivative equal to 0 and solve it. So we have the square root of 3 plus 2 cosine of t is equal to 0. So we've got to knock some dust off of those solving of trig equations that you did last year in either trigonometry or pre-calculus. We're going to obviously isolate the cosine function by square rooting dividing by the square root of 3 on both sides, and then that would be subtracting both sides by the square root of 3, and then dividing by 2. I was getting ahead of myself mentally of the steps we're about to do. Divide by 2. If we wanted all solutions, we would think about that first rotation around the unit circle, identify the 2 angles where the cosine function is yielding an answer of negative square root of 3 over 2, and then with each of those, and they're going to be in quadrants, quadrants 2 and quadrants 3, because that's where the cosine of an angle measure is the ratio of x over r. R is always a positive length radius, and the value of x, you could argue the length of x is always positive, but if we move left off of the origin, putting us into, am I doing that right direction for you? Yeah. Going to the left from the origin, our second and third quadrants are going to yield have x values which are negative. So we want angles that are in quadrants 2 and 3. If we want all the solutions, we would take each of those answers into a plus 2 pi n, where n is an integer, but we only want answers within that first positive rotation around the unit circle. So our answer is t is equal to what? 5 pi over 6, and t is equal to 7 pi over 6. Don't celebrate too much. That's not the end of our problem. I almost said, yay, we're done. We want the coordinates, and I'm running out of room. So let's clear this off a little bit. And for 5 pi over 6, we have h of 5 pi over 6 is equal to the square root of 3 times 5 pi over 6 plus 2 times the sine of 5 pi over 6. So we're looking at 5 square root of 3 pi over 6 plus 2. Now the sine of 5 pi over 6 is going to be, you're in quadrant 2, so y is positive. We're looking at 1/2. And our first point is going to be 5 pi over 6 and 5 square root of 3 pi over 6 plus 1. And our next point is going to be found by putting 7 pi over 6 in. Oh, let's just erase it. So we have 7 square root of 3 pi, pi is outside of the square root symbol, over 6. And then the sign of 7 pi over 6, now that we're down in quadrant 3 where these y values are negative, we're looking at 2 times negative 1/2. So our second coordinate is going to be at 7 pi over 6 and 7 square root of 3 over 6 pi minus 1. I should have just asked you for the x values where we have those horizontal tangent lines, but these are 2 pointed tangencies where we are going to have a horizontal tangent line for example 3. I'm Mr. True. Bam! Go do your homework.